SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the course Advanced Thermodynamics and Combustions, Module 3, Thermodynamic Property Relations. Till this point of time, we have completed 3 lectures, thermodynamic functions and Maxwell equations. Lecture number 2, property relations for phase change processes. Lecture number 3 is for property relations for single phase systems. We are now in the lecture number 4, which we are going to discuss today, that is heat capacity equations and its applications. So, in this lecture we will touch upon the following components. First is the fundamental thermodynamic equations what we have studied so far, we are going to summarize them. Then we will move on to another important equations or relations, which is known as TDS equations as well as heat capacity equations. Then we are trying to use this heat capacity equations for certain situations, and 2 situations we are going to discuss. One is for reversible isothermal change of pressure, second one is the reversible adiabatic change of pressures. Now, let us move to the topic of our discussions, that is the first segment, the fundamental thermodynamic equations. So, till this point of time we know that the classical mathematical concepts has been used to obtain 16 thermodynamic property relations, that includes Maxwell equations, and all these equations use the concept of exact differentials. Then we try to apply these equations for pure substances that accompany phase change process. So, there we derived Clapeyron equations and Clausius-Clapeyron equations. Now, when we apply these relations for a single phase regions in which we require at least 2 state coordinates out of pressure, volume and temperatures, and the most appropriate choice among these 3 are either temperature volume or temperature pressure. Then based on this we obtain one relations in which the properties u and s, u, s at p are regarded as a function of temperature and volume. Other relations we framed for temperature and pressures, and ultimately we told that all properties of interest for a pure substance can be determined as a functional form from the measured data through measured data which are pressure, specific volume and temperatures, and we can find the other derived properties using these relations. Now, let us understand what are those relations. First 16 relations that comes as a basic relations, Maxwell's equations and some additional relations. So, these 3 category called as 16 thermodynamic relations among the properties. Okay. Now, apart from that, so these are derived through our concept of exact differential equation. Okay. Now, when these relations are applied for phase change process, we get Clapeyron equations and Clausius-Clapeyron equations, and this Clausius-Clapeyron equations assumes the substance to be, when you deal with the change of situations or state at in a gaseous medium, we can assume this situation to be a equation to be constant, what is called as equation of state P v is equal to R T. Then this is about the these two relations are for phase change process. Now, for a single phase systems, we derived the relations for the mainly the specific heat at constant volume and specific heat at constant pressure as a function of the entropy and internal energy, and also we found the internal energy equations from these relations. Okay. Now, let us understand the next important segment at what we call as heat capacity equations. Many a times we all aware that the specific heat is one of the fundamental concept, and we see that specific heat means amount of energy required to change the temperature by unit degree Kelvin or centigrade. Now, we found that for substances like solid and liquid, we have one specific heat, but we specific heat for gases can have two. One is specific heat at constant pressure and specific heat at constant volume, because they follow the ideal equation, gas equation of states, where the change of state can happen through either at constant pressure or at constant volume. But what happens is that most of the laboratory experiments, when you define the specific heat capacity, normally it is done at constant pressure. So, in fact, when you tell that specific heat of water, by default it is assumed that we get the data when by keeping the pressure constant, and these laboratory data are reported. But what happens that when you go for the specific to find out the specific heat at constant volume, we normally ignore it, because it is very difficult to maintain constant volume while changing the temperature. So, there are experimental difficulties are involved. Now, because of these reasons, so it is required that we should also formulate the expressions in which we can find out the specific heat at constant volume mathematically for pure substances. So, this is the importance of these relations. Now, apart from that, we will be also using the some other important properties, which what we call as isothermal compressibility. In fact, we have already discussed about this in our previous lectures, and this isothermal compressibility is defined by the term kappa, that is equal to minus 1 by V into dou V by dou P at constant temperatures. Other parameter is volume expansivity or coefficient of volume expansion, beta, which is equal to 1 by V dou V by dou T at constant pressure. Okay. Now, having said all these things, let us try to see that how we can get the heat capacity equations. By heat capacity equations, we assume that we are looking at specific heats at constant volume and constant pressures. Now, from our previous relations, we can recall there are two important equations. One is ds is equal to Cv by T dt plus dou P by dou T at constant V into dV. Other equation is ds is equal to Cp by T dt minus dou V by dou T at constant P dP. In fact, this is one of the relations which I have noted in the earlier slide. Now, what you do is from these two expressions, if you subtract, that means if you find Cp minus Cv into dt, that means if you subtract ds will get cancelled. So, Cp minus Cv dt would be T times dou P by dou T V dV plus T dou V by dou T at dP. Now, at this stage we see that we have seen that it is a temperature, right, left hand side is the temperature, right hand side is the specific volume and pressure. So, we can to get all these relations we assume that, or we can say that if you say pressure is a function of temperature and specific volume, then we can find the expression of dP. Now, why do we require? Because we want to get rid of this dP. So, if you calculate this, so exact differential of pressure dP from these equations can be obtained as dou P by dou V at constant T into dV plus dou P by dou T at constant V into dt. Now, when I substitute this dP in these equations, then we get Cp minus Cv into dt and plus dt dou P by dou T at V dV plus T dou V by dou T at P, then dou P by dou V at T into dV, and last expression is T into dou V by dou T P dou P by dou T V dt. Then what you do? You simplify these equations. So, after simplifications we find these relations. So, right hand side of these equations contains only specific volume and left hand side of the equations contains the change in the temperature T. So, we have already mentioned that temperature and volume can be varied independently, so that by keeping other as constant. So, if you look at these equations, if you say there is no change in the temperature, but if you say the temperature change is not equal to 0, but specific volume change is equal to 0. That means, in a situation the specific volume does not change, but temperature changes. So, we get one expression Cp minus Cv is equal to T times dou V by dou T at P into dou P by dou T at V. This is first expression. Second expression, we can find out if dV is not equal to 0 and dt is equal to 0, then we can find out this dP by dt from these equations at constant V will be equal to minus dou V by dou T P into dou P by dou V at T. Then we arrive at, by substituting this dP by dt in these equations, then we get the expressions for Cp minus Cv is equal to minus T dou V by dou T P square into dou P by dou V at constant temperatures. Now, here if I recall the kappa as 1 by V dou V by dou P at constant T and beta to be 1 by V dou V by dou T at constant P. So, we can find that Cp by Cv, Cp minus Cv is equal to V times T beta square by kappa. Okay. So, basically the change in the specific heat is expressed in terms of isothermal, compressibility and kappa. Now, let us find out the some important consequences. But before I said this equation Cp by Cv, Cp minus Cv is equal to V times T beta square by K is often referred as Mayer equation. Now, what is the significance of Mayer equations? Let us find out the important consequence. First thing, so if I say this relation Cp minus Cv is this V times T beta square by kappa. Now, if here we have assumed that we have, and this relation is true for all the states of the substance, say solid, liquid and gas phase. Now, if I say in a situation that if your substance is an ideal gas where PV is equal to RT equation is valid, then we can find out dou P by dou V at constant T will be minus RT by V square, and dou V by dou T at constant P will be R by P. Now, when I put these expressions in the above relations, so Cp minus Cv stands as minus T R by P whole square or R by P into R by P and minus RT by V square. So, after simplifications we come across that Cp minus Cv is equal to R. R is nothing but the characteristics gas constant. So, here I need to emphasize that we all aware of these expressions Cp minus Cv is equal to R for an ideal gas, but this is the mathematical proof that how we get this Cp minus Cv is equal to R for an ideal gas. Now, in the second case, that is case 2, we are trying to prove that Cp is always greater than Cv. Why? Because the term beta square is always positive, even if is always positive because it is a square quantity, absolute temperature is positive and specific volume is also a positive number. So, this says that and in fact, more importantly that kappa is positive for all substances in all phases. This is an experimental evidence, and because of this reason we say that Cp minus Cv is greater than 0. So, or Cp is greater than Cv, which means specific heat at constant pressure is always higher than the specific heat at constant volume. And third important consequence we can derive that when the temperature T goes to 0, then it is the equation says that Cp minus Cv is equal to 0 or Cp is equal to Cv. What it means that at absolute 0 temperatures we do not have separate specific heat, we have unique specific heats, and because both Cp and Cv merge. And last important inference we can say that when dV by dt at constant P goes to 0, when dV by dt at constant P goes to 0, then only Cp will be equal to Cv, and this is this is true. This relation is true. dV by dt at constant P goes to 0 for solids and liquids. Okay. And so, because of this reason we say Cp is equal to Cv. One simple example says that when you say water at 4 degree centigrades, the density of water is maximum, and at that situation this tends to 0. So, this is all about the difference between Cp and Cv. Now, another important term we all are aware that we call this as a specific heat ratio Cp by Cv. Cp by Cv as is equal to gamma. This ratio we are trying to express in the form of isothermal compressibility to isentropic compressibility for the pure substance. Let us see how we are going to do that. That is first thing. Second important relations about this specific heat ratio is that this has a definite bearing with a property parameter which is known as speed of sound. In fact, speed of sound is a function of specific heat ratio for an ideal gas. We all know it. Now, let us see how we are going to get all these expressions. So, again here the first fundamental two equations we need to recall is the TdS equations. ds is equal to Cv by T dt plus dou P by dou T at constant V, and ds is equal to Cp by T dt minus dou V by dou T at constant P into dP. So, at constant entropy, that means ds is equal to 0. So, we get one relation Cp in the for Cp dt, other relation you get Cv dt. Then obviously, we need to find out the specific heat ratio, then you take this ratio. Now, when you take this ratio, of course, dou V by dou T term is here and dou P by dou V by dou T at constant volume term is here, and here this ordinary differential dP and dV, they becomes partial differential. Why do you say? Because that point of time we say it is happening, this equation is true for constant entropy. So, that is what we say dou P by dou V at constant entropy. So, then when you have this, then Cp by Cv ratio becomes dou P by dou V at constant S divided by dou P by dou V at constant T. Here we can see that entire relations between P, V, T, and it is a cyclic relations, and this term minus dou V by dou T at constant V divided by dou P by dou T at constant V comes to this expression, because B, P, V, T, they are in cyclic, we have used the cyclic mathematical relation. Okay. So, once you have this, then from these equations we say that dou P by dou V at constant S is equal to dou P by dou V at constant T into Cp by Cv. Now, we have arrived at these expressions. We are now going to recall the equations kappa, that is isothermal compressibility, and isentropic compressibility alpha. So, from these two equations we can also find out that when you put these equations here, the Cp by Cv relations is equal to kappa by alpha. How? Then what you do, Cp by Cv is equal to dou P by dou V at constant at S. So, this information you will get from alpha, and dou P by dou V at constant T will get this information from kappa. So, by putting this we get this relation Cp by Cv kappa by alpha. Okay. Again we say for an ideal gas Pv is equal to RT. So, we can say P is equal to dou P by dou V at constant T is equal to minus RT by V square. So, this equation we are going to use. Then next target was the how to find the another important property, what we call as speed of sound. So, speed of sound C is defined from its definition is that it is dou P by dou rho at constant S. Now rho is equal to 1 by specific volume, then the speed of sound is then expressed as minus V square dou P by dou V at constant S. Now, dou P by dou V expression you can get from alpha. So, we can say minus V square into minus 1 by alpha times V. So, after simplifying, then we can get speed of sound is equal to square root of Cp by Cv into V by alpha, V by kappa. So, V by alpha the Cp and dou P by dou V at constant S we can find out from here. Then from this we say that speed of sound is C is equal to square root of Cp by Cv into V by kappa. Okay. And for an ideal gas equations, this particular expression further gets simplified by considering these equations P is equal to RT by V and also dou P by dou V at constant S is equal to dP by dV at constant T into Cp by Cv. Ultimately, C becomes square root of Cp by Cv into RT. Okay. Now, we will move on to next important two equations, that is TDS equations, and we will find what are its important significance. In fact, when you talk about TDS equations, we already know these equations, but it has to be interpreted in a different form. And why we want to go for a different form? Because we are going to apply these equations for two situations. One is reversible isothermal change in the pressure, other is reversible adiabatic change in the pressures. We will see in the first category, that is reversible isothermal change in the pressure or at constant temperature. We will note down that dependence of specific volume and coefficient of volume expansion is insensitive to pressures for solids and liquids. Other important point we are going to note that the pressure, when the pressure increases isothermally, heat flows out, that means heat comes out, and for the substances for which beta is positives, and for substances with negative value of beta, we will see that isothermal increase in the pressure will cause heat absorption. The other important consequence we will find out is that isothermal compressibility is insensitive to the change in the pressure, and it is always a positive quantity, and because of these reasons this has linked with respect to work transfer, and this work transfer will be negative because it will be a compression situation. Now, when the pressure increases isothermally, the combined effect of this heat and work will have impact on internal energy. This internal energy is going to be increased. Now, when heat is absorbed, negative beta, and internal energy will drop when the heat is liberated. Now, these consequences, let us see that how we are going to prove mathematically. So, we will see, you can recall these TDS equations. TDS, in fact, here we will talk about the TDS equations in terms of pressures. So, we say you will use this equation ds is equal to Cp by T dt minus dou V by dou T at constant P into dP. Now, reversible isothermal change of pressure will lead to the fact this term will go to 0. So, we can say at constant T we can write these equations as TdS is equal to minus T dou V by dou T at constant P into dP. So, when you say TdS, it refers to heat transfer Q, which is equal to T times integral of dou V by dou T at P into dP. Now, this dou V by dou T at constant P we can find out from the expressions which is beta, and so that we can write this Q as integral of beta V dP. So, T can come out, and for many substances if you say this Q is a function of dP only. So, T beta V comes out. So, it becomes Pf minus Pi. So, Q is equal to T beta times V Pf minus Pi. Now, when the final pressure is much higher than the initial pressure, then this expression reduces to a simple one, Q is equal to minus T times beta V into Pf. Now, this is about the heat transfer. Now, for work transfer we have to recall the expression for kappa, where which we will talk about work transfer is integral of P dV. dV information we will get from this kappa. So, now after simplifying this we can write this work transfer W is equal to half kappa times B into Pf square minus Pi square. Now, when Pi is much less than Pf, so you can see what is the work transfer. W is equal to half kappa V times Pf square. So, in the information of Q and W one can find out also internal energy. The second case which we are going to study, what is the effect of reversible adiabatic change of pressure for pure substance. So, the word reversible adiabatic means it is an isentropic process. So, entropy remains constant, and here the inferences that we are going to get is that increase in the pressure will cause very negligible change in the temperature for solids and liquids, and Cp will be invariably constant, Reversible adiabatic change in the pressure will produce increase in the temperature for pure substance which has positive beta, and it decreases in temperature for negative values of beta. So, here also we recall the same equations, ds C is equal to Cp by T dt minus dou V by dou T at constant P into dP. Now, when I say adiabatic change of pressure, so entropy becomes 0, ds becomes 0, not entropy, change in the entropy is 0. So, from these expressions we can get Cp by T or you can say dt is equal to T by Cp dou V by dou T at constant P into dP. Now, this dou V by dou T at constant P information we will get from the value beta. So, after putting this we get the temperature change when there is a increase in the pressure, and this happens when at constant entropy. So, the rise in the temperature for the pure substance can be expressed as a function of is equal to T into beta V by Cp into Pf minus Pi, and when this Pi is much less than Pf, we will see that the delta T becomes T beta V by Cp into Pf. Okay. So, this is all about the contents for the lecture today. Now, we will try based on the content we have discussed, we are going to solve some simple numerical problems, and here I say simple because all the expressions we have already has been derived in these previous slides. So, I will note down these expressions directly. So, intended audience, you can please refer the slides for the derivation of the equations. So, the first problem talks about the last two segment of our discussions, reversible when there is a when the pressure is increased in a reversible isothermal manner for a pure substance, and when the pressure is increased in the isentropic manner. So, we have the problem that is given, we have 2 centimeter cube mercury which is available to us as 25 degree centigrade. So, you have this mercury in a container and it is volume is 2 centimeter cube and it is temperature is 25 degree centigrade, and this is available to us, and we need to find out this pressure is increased to 1000 bar. So, final pressure becomes 1000 bar. Okay. So, we need to find out through this change in the pressure what happens to Q and what happens to W. So, first thing we can say that based on our understanding or assumption, when work is done by the system, it is taken as positive. When heat is added to the system, it is also treated as positive. Okay. So, based on the data we have for mercury, we have the data beta and kappa. What is we need to require? We need to find out Q, W and delta E. So, this is a case where pressure is increased in a reversible and isothermal manner. So, we can recall our expressions derived in the previous slides. Q is equal to T times V beta into Pf. Okay. So, here T is 25 degree centigrade, that is 298 Kelvin. V is given as 2 centimeter cube, and that is 2 into 10 to the power minus 5 meter cube, beta is given, kappa is given, and Pf is 1000 bar. So, we can write it as 1000 into 101,325 Newton per meter square. So, by inserting this value we get Q is equal to, and here it is minus, T is 298 into 2 into 10 to the power minus 5, beta is 1.8 into 10 to the power minus 4, Pf is 101,325 into 1000. And this one after simplifications we get Q as minus 108.7 joule. Okay. And since this is negative, we say that heat is absorbed. And second expression, we can use this W as minus half V kappa into Pf square. So, all these numbers are given. By inserting these values, we can say W would be minus 4.1 joule, which means work is done on this system. That is also true because we are increasing the pressure, and this difference, this from this we can get delta E as summation of these two is minus 112.8 joule. So, this means internal energy goes into the systems, that is increase in temperature. Okay. So, this of course, these numbers Q delta E are very small with respect to quantification of increase in the pressure by 1000 bar. So, it means that mercury is very insensitive to these changes. In fact, this is also clear from the values of beta and kappa defined for mercury. And next problem is in relation with the first problem, but here the association was reversible and adiabatic manner the pressure is increased. So, same mercury, we may have this mercury in a container, and this container is insulated. So, Q is equal to 0, pressure goes to 1000 bar, and its initial pressure Pi is atmospheric 10 to the 5 Pascal, and all other numbers given, that specific volume, Cp, beta and kappa. So, we want to find out the change in the temperatures. So, let us see the first part of the problem A, where we derive this expression change in the temperature is equal to T times specific volume beta divided by Cp into Pf. All these numbers are given. T is 25 degree centigrade, that is 293 Kelvin, and beta is given, specific volume is given, Cp is also given, and Pf is 1000 bar, that has to be expressed in terms of SI unit in terms of Newton per meter square. So, we will have to insert this value, where we can say delta T will be 298 into 7.4 into 10 to the power minus 5, beta will be 1.8 into 10 to the power minus 4 divided by 0.15 into 1.01 into 10 to the power 8, okay, because you have this is in the kilojoule. So, delta T we can find out as 2.67 Kelvin. We say that mercury is very insensitive to this change in the pressure. Although you have increased the pressure by 1000 bar, but hardly temperature change is recorded about 2 degree Kelvin. And second part, again we say that when the volume is kept constant and temperature is raised by 10 degree centigrade. So, for that we have not derived these relations which we are going to do now. So, we can say if P is equal to function of temperature and volume, then we can find out dP is equal to dou P by dou T at constant volume dV dt plus dou P by dou V at T into dV. So, here we say keeping volume constant. So, this term goes to 0 and this information we require. So, for that we have to recall beta is equal to 1 by V dV by dt at constant P, kappa will be minus 1 by V dB by dP at constant T. So, from these relations we can find out dP. Now, if you say cyclic relation between P, V and T, then from this we can get dP by dt at constant V will be equal to beta by kappa. So, from this we can say delta P will be equal to beta by kappa into Tf minus Ti. Ti is already given 293, beta is given, kappa is given. So, from this we can find out, and delta P is equal to Pf minus Pi, and Pi is 10 to the power 5, and from this we say delta P is Pf minus Pi, and from this we can find out final pressure would be about 452 bar. So, what it says is that if the temperature of mercury is raised by 10 degree centigrade, keeping volume constant, we require 452 bar for this change in the temperature. That is because this value of beta and kappa value is very less. That means mercury is typically insensitive. And the last problem that we are going to discuss is about the relation between Cp and Cv. So, the problem says that what is the error in Cv for water. I mean, we are considering water at 1 atmosphere and 20 degree centigrade, if Cp is equal to Cv is assumed. Now, whether this is logical or not. So, this you have to find out. Second part of this problem is we have to find out the specific speed of sound as a function of specific heat ratio. So, the relations that we have to recall is, first relation is Cp minus Cv relation. So, we recall Cp minus Cv is equal to V T beta square by kappa. Okay. Now, what we do not know is, we know beta and kappa, and at 20 degree centigrade what we know is rho, that is 998 kg per meter cube, and rho is nothing but 1 by specific volume. And also at 20 degree centigrades we know that what is the Cp for water, 4.188 kilojoule per kg Kelvin. Okay. So, these two information you know, and T is 20 degree centigrades, that is 293 Kelvin. Now, when I put this number, then we can say Cp minus Cv is equal to 1 by 998.2, T is 293, beta that is 0.2 into 10 to the power minus 3 whole square, kappa is in the bar. So, we need to find out, we need to express in terms of Newton per meter squares. So, we have to multiply 101.325 divided by 49.6 into 10 to the power minus 6. So, after simplifications we get Cp minus Cv is equal to 0.024 Kelvin. So, you already at the data Cp. So, this will give you Cv value as 4.164 kilojoule per kg Kelvin. So, the question arises that what is the percentage of error in Cv. So, we can now say Cp minus Cv by Cv ratio. If you want to find out into 100, then we can say this is 0.024 divided by 4.164 into 100, that is equal to 0.5%. So, basically if you assume Cp is equal to Cv, we will land up in 0.5% error. So, it is by default we say Cp is approximately equal to Cv, and that value is assumed it as a 4.188 kilojoule per kg Kelvin, and this is taken the experimental data which is recorded at constant pressure. So, this is the first part of the problem. Second part of the problem is very simple. I have already derived the relations for speed of sound c, and this is equal to square root of Cp by Cv into V by kappa. So, these relations were already derived in the earlier slide. So, you just have to insert the data, that is Cp is 4.188, Cv is 4.164, specific volume is 1 by 998.2, kappa is 1 by, that is 101.325 divided by this number 49.6 into 10 to the power minus 6 entire square root. So, ultimately we will get speed of sound is 1434 meter per second. The speed of sound, and that is in the for the water, in the water medium. So, with this I conclude the lecture for the today. Thank you for your attention.